at the beginning of last week. So that's where we've got a variable in the denominator. Now we're going to be graphing those, and a lot of this has to do with finding asymptotes and domain restrictions and end behavior we're going to talk a lot about in this section. This is also what your circuit training this week is over. You're going to see some rational functions and asymptotes information on there. All right, so we are going to start with what makes a rational function. This is just its definition. So if a numerator and denominator both meet the definition of a polynomial, if you have a polynomial divided by a polynomial, you have a rational function. So that's why it is in this section. We've been doing all the different things we can do with polynomials, solving them, graphing them. We've seen the equations where polynomials pop up as well. And now we're going to divide them, which gives us these rational functions. Okay. Because we are dividing, because there's going to be variables in the denominator, we will have domain restrictions. And in most cases, those domain restrictions are also going to be our vertical asymptotes. So what we're going to do to find vertical asymptotes is we are going to factor our numerator and denominator completely and reduce it. Cancel out any common factors. We've practiced doing that before. Once it's reduced completely, anything that's left in the denominator as a domain restriction will then be your vertical asymptote. Now, if you remember vertical asymptotes, horizontal asymptotes from previous math classes, these are lines we're writing the equation of. So a vertical asymptote is a vertical line that our graph is going to get really close to but not touch. So it's important that when you write the equation of it, it starts with x equals. It's a vertical line. And then horizontal asymptotes are going to start with y equals, and it's going to be a horizontal line that our graph gets really, really close to but does not touch. Okay. All right, so I think the first thing that we're going to do is on your big idea worksheet, we're going to practice finding some vertical asymptotes. We're going to do it together here. All right, so are these on your paper? Yes, good, okay. So find the vertical asymptotes and then name the domain. All right, so to start, we need to factor completely our numerator and denominator. The numerator in this first problem is a linear equation, so it's not going to factor at all. The denominator, though, can factor a little bit. When we've got two perfect squares and a minus between them, remember we call that difference of squares. What does it factor to? Good, conjugates, x plus 2 and x minus 2. Okay, and then if you want, you can even put the numerator in parentheses, make it pretty. Do I have any common factors? Yes, x plus 2 is a common factor, so it cancels. What am I going to be left with in the numerator? Denominator x minus 2, numerator just a 1. Nothing's left up there. Okay, so now my rational function is reduced completely. Anything now that would give you a domain restriction in the denominator is a vertical asymptote. So really all we're doing is setting our denominator equal to 0 and solving, and we get x equals 2 is the vertical asymptote. Make sure you put x equals in front of it. That's a common mistake, just giving the number, not the whole equation. It also says here to name the domain. The domain is any x value that would give you a 0 in the denominator in the original function. So we're not looking at the reduced one here. We're looking at the original one, and you can maybe look at the factored version of it that we have here. So definitely a vertical asymptote is a domain restriction. It's going to be a line that we're not going to be able to cross. But then we also have this x plus 2 in the denominator, which means what else is a domain restriction? Negative 2. So my x's cannot be plus or minus 2. So now we want to put that domain in interval notation. So think about a whole number line, all real numbers graphed, except we have an open circle at negative 2 and positive 2. So it's going to break my number line into 3 different groups. And those groups are negative infinity to negative 2, negative 2 to 2, and 2 to infinity. Now, what does it mean when we have a domain restriction, but it's not an asymptote? That means that you have, and I think it says this at the bottom of your paper, a hole at that point on the graph. So it means you're going to see the curve. Holes, by the way, are really difficult to see with your graphing calculator. You're going to have to find these in the equation. you're going to have a curve, and then in the middle of this curve, there's just going to be this open circle wherever x is -2 at. Okay, and we'll see a couple of those when we do some of the graphing tomorrow. So not a vertical asymptote, but an open circle located somewhere on the graph if you've got that value that cancels out. All right, let's try the next one. X plus 1 over x squared plus 3x minus 10. Does my numerator factor? What would it factor to if I factor my numerator? Oh, you think denominator? There we go. You're right. -2 and 5. And then numerator is linear, right? So just x plus 1. Put in parentheses and make it pretty if you want. Do we have any common factors? Nothing reduces, which means any domain restriction will also be a vertical asymptote here. So we have vertical asymptotes at what numbers? X equals 2 and x equals -5 if I set each of those factors equal to 0. Domain then is just going to match up with that. Everything except 2 and -5, which in interval notation would be -infinity to -5, -5 to 2, and 2 to infinity, and everything there is parentheses. Okay. Questions finding domain, poles, vertical asymptotes. That's how we're going to do it. Nothing crazy. Okay? Good there? All right. So the next little piece we're going to add on today is how to find a horizontal asymptote, because these graphs will potentially have both. Horizontal asymptotes have 3 sets to the rules. Now these are straight out of your textbook, how these are written, so I'll kind of explain them. So one of 3 things is going to happen, and it's all going to be based on the powers in your numerator and denominator, your degree of your numerator and the degree of the denominator. The degree of the numerator, they're calling n, and the degree of the denominator, they're calling m. So you're going to need to find the highest power in both your numerator and denominator, and you're going to compare them. And one of 3 things can happen. The numerator is greater, the numerator is equal to, or the numerator is less than the denominator. And that makes up the 3 cases here of what can happen. If n is less than m, if the degree of the numerator is less than the degree of the denominator, the x-axis, or y equals 0, is the horizontal asymptote. There is no calculation necessary. If n is equal to m, y equals a sub n over b sub m is your horizontal asymptote, which is a fancy way of saying divide the leading coefficients. Take the leading coefficient in the numerator, take the leading coefficient in the denominator, divide them, and y equals that number, whatever it is, will be your horizontal asymptote. So maybe for this one, note to self, those are the leading coefficients of the numerator and denominator, that a and b. And then finally, if n is greater than m, there is no horizontal asymptote. That is the case where we will have an oblique asymptote, which means a diagonal asymptote instead, and we'll talk about that a little later on. So for right now, if you were finding horizontal asymptotes and n is bigger than m, you would just say none. Okay, so make sure you have these 3 cases. N is less than m, horizontal asymptote, y equals 0. N is equal to m, y equals, divide the leading coefficients. N is greater than m, there is no horizontal asymptote. It will instead be oblique. Everybody got what they need? All right, let's practice on your big idea worksheet. Find the horizontal asymptotes. So we're going to start by finding n and m. N, degree of the numerator, m, degree of the denominator. What is the degree of the numerator in this problem? 1. Power of 1 is my highest power there. And degree of the denominator is also 1. They're both linear. So we have the case where n equals m. So we're looking at case 2 that you just wrote down. If n equals m, my horizontal asymptote is y equals, and then we're going to divide the leading coefficients. What's the leading coefficient of the numerator? What's the leading coefficient of the denominator? 3. That does not reduce. This is your final answer. Y equals 2/3 is the horizontal asymptote. Okay. Second one, degree of the numerator is 2. Degree of the denominator is 1. So we have the case where n is greater than m. So if I ask you what's the horizontal asymptote, your answer should be there is none. And instead, you can write the word oblique there. We'll talk about that later, what that means. Okay. Finally, degree of the numerator, and this last one is degree of the denominator is n is less than m. So my horizontal asymptote is y equals 0, or the x-axis. Okay. Make sure whenever you're naming an asymptote, it's either going to start with x equals or y equals, depending on if it's vertical or horizontal. Questions there? All right. Third, well, I take that back. Yeah, third. This is not on your big idea worksheet. Third type of asymptote we're going to talk about is an oblique asymptote. We just talked about when it occurs. It's going to occur when n is greater than m. How we calculate a oblique asymptote is we divide. Numerator divided by the denominator. The quotient, when we divide the numerator and denominator, is an oblique asymptote. Stick a y equals in front of it, and you have this diagonal asymptote, is what oblique means that we're going to get. Okay, so instead of a vertical line, instead of a horizontal line, we're going to get a diagonal line. It does not matter what your remainder is here. We do not have to get a 0 remainder to calculate an oblique asymptote. So numerator divided by denominator, and you could, depending on what numbers you're given, either use long division or synthetic division. If you're dividing in a linear term, I would use synthetic division. If you're dividing in something bigger than that, you have to use long division. The quotient is the oblique asymptote. So we're going to do this problem. Move it up a little bit for you here, maybe. Here we go. Okay. And we're going to find any asymptotes. We're going to do all 3 of the cases. All right. So first things first, I want to factor it to see if anything reduces. Does anything factor here in my numerator? What factors in my numerator? An x. That would leave me with what? X plus 1. And my denominator is x minus 1. Put it in parentheses, make it pretty if you want. Are there any common factors? There are no common factors, nothing reduces. All right, so we don't have to worry about getting a hole on the graph eventually. The next thing we're going to look to find are vertical asymptotes. Where do I find my vertical asymptotes? Denominator. So what is the domain restriction in the denominator? If you said x minus 1 equal to 0, you get x equals 1. That's my vertical asymptote. X equals 1 from the denominator. Okay, then we kind of do horizontal asymptotes and oblique asymptotes together. It's either one or the other. It will not be both. In either case, we compare n and m. What is n, the degree of the numerator? 2. M, the degree of the denominator, is 1. N is greater than m. So there are no horizontal asymptotes, and instead there is an oblique asymptote. So now how we calculate it is we're going to literally do the division we see. Numerator divided by denominator. Am I allowed to use synthetic division this time? or no? Yes, right? Because my denominator is linear. So as long as you've got a power of 1 in that denominator, you can use synthetic division. If you get something bigger than that, you have to use long division. All right, so let's set up our synthetic division. Powers, starting with 2, I have a 1 for my leading coefficient in front of the x squared, a 1 in front of my x, and then there's no constant term, so I'm going to put a 0. What number is going to go in the box for my synthetic division? If I'm dividing in x minus 1, if I'm, set it equal to 0, 1. Okay, the quotient is what's going to give me this oblique asymptote. Bring down my 1, multiply 1 times 1, 1, 1 and 1, 2 when I add. 1 times 2, 2, add them together, 2, the last number is the remainder. It does not matter what the remainder is. We're going to just throw it out. We don't need it. Okay, so I had a degree 2. I did synthetic division 1 time, which means when I put my variables back in, it's now degree 1. This is linear. X plus 2 is what I'm left with. Stick a y equals in front of it, and that is your oblique asymptote. Most of the time, this will be a line, but depending on what you're dividing in, it could even be like a parabola that's an asymptote. If I had like a degree 3 on top and a degree 1 on the bottom, we could approach a curve instead of a line. So these get kind of interesting. We don't go super crazy with these. We don't see them very often. And in fact, most of the ones you guys do in Math Excel, you'll be able to use the calculator to get the sketch of it. But I do want to show you where those come from. You might see 1 or 2 problems where you have to actually calculate them. Okay? Questions on that? All right. Last thing today is end behavior of rational functions. So we talked about end behavior before with polynomial functions. Polynomials are continuous. There's no breaks in the graph, so we only ever had 2 ends. One on the left, one on the right, and it either went up or down. Those are the only 2 things that happen with polynomials. Rational functions, as soon as we start to throw in asymptotes, they now have extra ends. There's more arrows. Anywhere that there's an arrow on the graph where it breaks apart from one piece to the next is now considered an end behavior, and we have to list them. So sometimes you might see 2, like the polynomials. Sometimes you might see 4, like these pictures. Sometimes you might see 6. It depends how many asymptotes you have on the graph. Now, the left and the right are going to look exactly like we did with polynomials. X approaches negative infinity, x approaches positive infinity, and then the y is going to approach either infinity or negative infinity. It could also, in most cases with these, approach a horizontal asymptote. So like here, I would say maybe my y is approaching 0, because it's not going up forever, it's not going down forever, it's just getting really close to that x-axis. In the middle is where it's going to get fuzzy, because our x isn't approaching negative infinity or infinity anymore. It's approaching that vertical asymptote. So when we list these, so here, for example, they're giving you a value of a, is that vertical asymptote. We might say x approaches a, and then y approaches, maybe for the one on the left side, infinity. Because as we get closer and closer to a, it goes up forever. It also does the same thing on this side. As we get closer and closer to a, it goes up forever. Graphs like this, though, cause a problem, because on one side, as I get close to a, it's going down, and on the other side, as I get close to a, it's going up. So we need a way to distinguish this is happening on the left side of the asymptote, and this is happening on the right side of the asymptote. So what I would write for a graph like this, and we'll practice a couple of these today, is I would say as x approaches a on the left, we're going to put a little, it's going to look like a little negative symbol up in the exponent. So that means I'm on the left side of the asymptote, and then we say what y is approaching. Well, on the left side of this asymptote, it's going down forever. So I would say y is approaching negative infinity. And on the other side, I could say x approaches a again, but this time we're going to put a little plus in the exponent, meaning I'm on the right side of that asymptote. And on the right side, as I get closer and closer to the asymptote, it's going up forever. So I would say y approaches positive infinity. So every end behavior is still going to have an x with an arrow and a y with an arrow. X approaches, y approaches. The only difference is now they might not all be infinities. Your x might be approaching an asymptote, a single number, or your y might be approaching an asymptote, a single number. And if you're approaching a vertical asymptote, we're going to need to put a little plus or minus up in the power to distinguish if we're on the left or the right side of it. All right, so we're going to do this next picture together, and then you guys are going to practice on your big idea worksheet in a minute, okay? So I have a graph of a rational function here. We are going to name 6 end behaviors from this graph. We're going to give its domain and range, vertical asymptote, horizontal asymptote, all the things from the picture. All right, so I am going to number my ends here. So 1, I'm just going to go from left to right. 2, 3, 4, get out of the way, 5, and 6. Okay, so 6 ends that I have to name. For each of them, I have to say what x is approaching and what y is approaching. For the one on the far left, what is x approaching? Left and right. If you go further to the left, what are you approaching? Negative infinity for the x. All right, so we're looking at this guy at the bottom here. X approaches negative infinity. As my x gets closer and closer to negative infinity, as this graph goes further to the right, what is the f of x, the y, approaching? It's getting closer to that horizontal asymptote at 2. Okay, and while we're at it, let's do the one on the far right, number 6. For that one, my x is approaching positive infinity. It's going forever to the right. And as we go further to the right, what is my y approaching? Also the horizontal asymptote, 2. So now we're going to talk about each of those vertical asymptotes, starting with number 2 at the top. My x, left and right, is getting closer and closer to the vertical asymptote at negative 3. Am I on the left or the right side of it at the top there? I'm on the left side of it. So it's going to be negative 3 with a little negative up in the exponent, which is the first one that's written there. Okay. And as I get closer and closer to that asymptote, what's my y doing? Is it going up forever? Is it going down forever? Is it getting closer to a single number? It's going up forever. Y is approaching positive infinity. On the other side of that vertical asymptote, I've got end behavior number 3. This guy's on the right side of negative 3. So that's going to be this next one, negative 3 with a little plus. Tells me I'm on the right side of negative 3, and what's the y doing there? It's going down, negative infinity. End behavior number 4 is on the left side of 3. So I'm looking for x approaches 3 with a negative. Right there. My y is going down, negative infinity. And finally, end behavior number 5 is on the right side of 3. So I'm looking for x approaches 3 with a little plus in the exponent. It's the last guy I have here. And that guy's going up, positive infinity. Okay. Let's talk about domain and range. What are the domain restrictions? X cannot be what in this picture? Plus or minus 3, the vertical asymptotes. Are there any other holes in the graph, open circles that we see? No. So my domain is negative infinity to negative 3, negative 3 to 3, 3 to infinity. Range, you're just going to read off of the graph, bottom to top. What's the lowest this graph goes? Negative infinity. And then that kind of U shape at the bottom goes all the way up to what y value and then stops. 2/9. Would 2/9 have a bracket or a parentheses? It would have a bracket because I do have a point there. It's labeled. Then it jumps to what y value? Or really close to what y value? 2, because it's an asymptote, it's going to be a parentheses, and then it goes all the way up to infinity. So those are those little kind of branches, we call them at the top. Vertical asymptotes, we already named them. X equals 3, x equals negative 3. Horizontal asymptote, we already named it, y equals 2. All from the picture. Okay, you guys have one on your paper that is just like this. I'm going to leave this up on the board for you. I used little images to match them up for you, okay? So I labeled each end behavior with an image. Next to that image over to the left, I want you to list the end behavior. And so you might want to start with just an X and an arrow and a Y and an arrow. That's got to be for every end behavior. X approaches, Y approaches, and then you're just filling in the numbers or the infinities that go along with it. Okay, work with your groups. I'll give you like, I don't know, 5 minutes or so. We'll put the answers up on the board probably. I'll put each of you guys in charge of something, and that'll be it for today then. We'll put all this together tomorrow with a graph.